We're going to wrap up our discussion of bipartite graphs for the time being. We'll use them again, but we'll wrap them up with the mention of Hall's marriage theorem. And the point of Hall's marriage theorem is when can you, using the edges of a bipartite graph, match each person in one of the bipartition sets to a person in the other set in such a way that two in the first set are not matched to the same one in the second set. So in other words, in other language, right, this is a one-to-one function from V1 in the bipartition to V2 that maps each element of V1 to an element of V2 that it's adjacent to. And the one-to-one means that you're not having two people in V1, two vertices in V1 matched to the same vertex in V2. So that's what this all says here. And if we have such a matching, it's called a total matching from V1 to V2. I'll give you a sketch of one of these after we talk a little bit more about it. Of course, for this to be possible, then every vertex in V1 has to have positive degree, so there is an edge to follow to V2, but there's more than that that's required. In fact, it's a little bit more of a general idea than that. If we take a subset E of V1, then we'll use N of E to refer to the neighbor set of V, meaning the set of all vertices in V that are adjacent to at least one vertex in V1. So this is more general than just for a bipartite graph, but that's all we need it for right now. So N of E just means all the vertices that are adjacent to something in E, at least one vertex in E. So the theorem that Philip Hall proved, called the marriage theorem, because you can think of these two sets as people who are looking for a mate, maybe a set of men and a set of women, in a traditional way of thinking about this. And that's where the term comes from there. But it's really a matching theorem. A bipartite graph with the bipartition V1, V2, so those are the two sets, so that any edge goes from V1 to V2 and not within V1 and not within V2, has a total matching of the type we were talking about from V1 to V2. There is a directionality here, right? We want everything in V1 to match up with something in V2, but we're not insisting on the other way, that everything in V2 is matched up with something in V1. Such a total matching exists if and only if the number of neighbors of a set of E is always at least the same number of elements in the set or more. Let me show you a case in point here, just as an example to start off with. So suppose we have V1 has four things, four vertices, and V2, those are kind of close together. Let me try that again. V1 has four vertices, and V2 has, let's just make it four as well, like so. And I'm going to draw the edges here, maybe something like the following. So I'll draw these edges here. And like so. And I don't know, maybe I'll draw another edge there and an edge there. So there we have a graph there, and there's V1 and V2 down here. And now you can quickly check that if you take any singleton set, the number of things it's adjacent to is at least equal to 1, right? So if E is just a singleton, like A in here, then the neighbor set of A is at least as big as the set singleton A itself, which is 1, right? Whatever A is here, that's going to work out. I'll call that one A. In that case, you get 2 for the neighbor set. There are 2 things in the neighbor set. The 2 things down here are the neighbors of A, right? Right, so in fact you can check and see that it works for doubleton sets too. So for example, if you look at AB, then the neighbor set of AB where E is AB, is equal to, let's call this W, X, Y, Z down here. The neighbor set of AB would be X and Y. So X and Y. And so the neighbor set of AB is 2, which is greater than or equal to, it's exactly equal to, the size of the set itself, X, Y. Right, so it works there. In fact, any two will work out. If you take A and maybe C, you get 2 there. If you take A and E, you get 4 there, and so forth and so on. But if you take 3 in a set, it fails. In this case here, if we take this set of, say, ABC, then the neighbor set of ABC is only X and Y, and there's no hope for each of A and B and C to be matched up to unique elements in V2, so it fails there. So it's easy to see why it has to fail. Proving that it's true requires an induction that's a little lengthy, involves strong induction. So we're going to not prove it, but it's an interesting result in graph theory, just to show you this kind of a result here. Now, as we move along, we'll leave the bipartite graphs for now and talk about what a directed graph is. A directed graph is just basically a graph that has edges that are directed from one vertex to another. So that's what we call a digraph or directed graph. And I'll use D for that often, for the digraph, first letter of that. So it has a set of vertices, just like a graph, and a set of directed edges now, which we might call arrows, each of which is associated with 1 or 2 vertices as before. So if it's 1, it's going to be a loop, right? And if it's 2, then it would be directed from an initial vertex to the terminal vertex. That would be the direction of it. So if there aren't multiple edges, then we can use an ordered pair to indicate a directed edge if we want to talk about it aside from the sketch itself, because the ordered pair itself gives us an order from A to B. And then if we have more than one from A to B, you can do it. It's not too hard. We could subscript one of them with 2 and a second one, with one of them with 1 and the second one with 2, so that that would be a labeling scheme to continue on with for multiple edges if need be. Just as we had the degree of a vertex in the graph before, we will do the same thing here, except we'll have the in degree, which is the number of directed edges that have the vertex as a terminal vertex. This is pointed in, so that's the in degree right there with the minus pointed in. What I mean by that is the edges that are pointed in, and the out degree is the edges that are pointed outward. Okay, and that's a plus for away, for outward. So let me draw an example, and we'll do a little bit of calculation on this. So let's take a graph that looks like this. I'm gonna just have 5 edges here, maybe, and maybe one taken off to the side someplace like so. So it'll actually have 6 vertices and I guess 6 edges, it turns out. Oh, let's put some more in here. Let's put that one there and that one there, and let's go ahead and call this A, B, C, D, E, F. And now I have to put some directions on there, so I'm going to just kind of do this without a whole lot of thought involved here. Do that right there, and then that like so. So there's our directions on there as well. And so for a table of degrees, we might put the following. Let's put the vertex and the degree minus and the degree plus, like so. So we would have A, B, C, D, E, F, and for A, the number of vertices, edges pointed in is the in degree. There are 3 of those. That's 3. And there's 1 pointed out, right? So the in degree is 3. Those 3 pointed in like so give us the in degree. And the 1 pointed out gives us the out degree. So, one of those probably gives you the story. You could fill in the rest here and maybe do that as we pause and then come back in a second. I'll carry on with B. So B has 2 pointed out, but none pointing in. So 0, 2. C has 2 pointed in, 1 pointed out. D has 2 in and 1 out. 2 in and 1 out. E has 3 out and none in. 3 out and none in. So none in and 3 out, I should be saying in that order. F has 1 in and none out. So let's just add those up and see what we get for those sum of the degrees, the in's and the outs. And so in this case here we get 4 and 4 is 8. In this case we get 4 and 4 is 8. We get 8 in both cases. Do you always get 8, the same number in both cases? The answer is yes, and that's the context of the theorem below. And the reason is, if we just take one of these to talk about, for example, maybe we'll take this edge right here, the edge from B to C. The edge from B to C counts 1 in the out from B. So it counted 1 over here, and that same edge counted 1 towards the in degree of C. So each edge counts exactly once in both places. This is the edge B to C. This is the edge B to C here. And so this is the number of edges. By that same sort of logic in general, each edge counts twice, once towards the out degree of the initial vertex, once towards the in degree of the terminal vertex. And so we have this result here that in a digraph, the sum of the in degrees equals the sum of the out degrees is equal to the number of edges. All right, I think we'll stop that here.